Example 2. We have a periodic signal, which looks like this. And from the figure, you can tell that the period of this signal, the fundamental period of this signal is how much? It's pi, right? The fundamental period is pi, just from the figure. And the function itself between 0 and pi or over any period is exponential minus t divided by 2. And we want to find the the Fourier series coefficients for this signal. So we want to write this signal like this, xt. We want to write it as a summation of some coefficients scaling the harmonics of this signal. Okay, from minus infinity to plus infinity. Now, those coefficients are given by 1 t naught integration over 1 period xt exponential minus j k omega naught t dt. So, as we said, the period of this signal is pi, and then omega naught is 2 pi over pi, which is 2. Right? Now, if we substitute omega naught and t naught here, we get 1 divided by pi, and the integration, let's do it from 0 to pi. So spanning 1 period of the signal from 0 to pi. And then the signal itself, as it's defined in the question, is exponential minus t divided by 2. So exponential minus t divided by 2 times exponential minus j k omega naught t dt.
I have a quick question.
Okay, go ahead.
So would it be like beneficial? Like, is it better to leave the omega naught by itself before you plug in what you calculated for omega naught, or could you just plug it in like before you take the integral?
It depends. Maybe keep it till the end, yeah, and plug it in, because sometimes if it's similar to here, omega naught is just 2, and it won't matter that much. But if omega naught is something like pi times something, and then at one point you'll get exponential j omega naught k, let's say. And if you put pi here, then you can simplify this term, right?
I see.
Because this will be cosine. Let me write it in a better way. And this will be cosine omega naught k plus j sine omega naught k. Now, if we put the omega naught equals pi here, we will be able to simplify this term, right? Because cosine at pi is -1, right?
Yes. Yeah. Yeah, I see now.
And then at 2 pi is +1. But the sign is always 0. This term is always 0. right?
Right. Yeah,
For
I
any
get it.
k. Yeah. And this term would be just minus 1 to the power k, right? To alternate between plus 1 and minus 1.
Right, right.
Yeah. So in this case, yeah, sometimes it's better to plug it in before just to simplify those terms if they appear, or depending on the value of the omega naught. Uh, but yeah, in general, it will not matter that much in general. Yeah. I'll keep it in this example. I'll not plug it in here. So let's combine those two terms. So we have 1 divided by pi, 0 to pi. It will be exponential minus 1/2. I'll take the t outside. 1/2 minus j k omega naught t dt. Now we just do this integration. Simple one. 1 divided by pi. Then minus 1. This is a multiplication. It's not x. Let me multiply them. So the minus would be here, and then we'll have 1/2 minus j k omega naught. Then the exponential 1/2 minus j k omega naught t between 0 and pi. Now, I think, yeah, here if we plug in the omega naught is better. Do you see why?
Yeah,
Yeah,
yeah.
because we will get 2 pi here, and we can simplify. Minus 1 divided by pi times 1/2 minus j k omega naught. And then here we have exponential minus 1/2 minus j k. I'll plug in omega naught, so it will be 2. This is j, and this is pi minus exponential 0. This is 1. Here we have 1/2 j k omega naught. Here, if we split those two terms, it will be exponential minus 1/2. We multiply with pi, exponential minus pi divided by 2 times exponential j k 2 pi minus 1. Okay. I have yeah, this should be plus, right?
Yeah, it should be.
Yeah,
I
it should
think.
be plus. And here it will become negative again. Yeah. Now this one is just 1, right? Do you see it? Because it's cosine minus 2 pi k plus j sine 2 minus
Oh,
2
right. Yeah.
pi
Okay,
k.
that makes
Yeah.
sense.
This one is always 0, no matter what k is. And this one is also always 1 because of 2 pi. And then multiples of 2 pi will make the cosine always positive 1. So this will be just 1. So what's left here is minus 1 divided by pi times 1/2 j. Oh, there's a minus here. Yeah. Minus j k omega naught j k omega naught. And then here we have exponential minus pi divided by 2, and this would be 1. It's minus 1. Okay. Minus 2 pi. I think I have also, yeah, since yeah, when we corrected this, it was minus and I made it plus, right? Now those will be plus, right? Correct, right?
Wait, can you say that again? I'm trying to see it. Ugh. I mean, like trying to understand it. That's what I mean.
Because I initially I had a mistake here. I have written minus instead of plus. So when
Oh,
I did the
right.
yeah,
Sorry. I wasn't
when I
keeping
did the
track of.
integration, yeah. So I corrected here. I should also correct it here.
Okay, yeah, that makes sense. I was focused on like the other things that you were doing, like the cosine of negative 2 pi that I didn't notice the integration. My bad.
Oh no, it's okay. It's actually my bad. But yeah, sometimes it's easy to make mistakes. And then let's just simplify a little bit. We can multiply by 2 here, and then also submit as plug in this omega naught. Actually, we should have done this from this step from here. When we plugged in omega naught here by 2, we should have done it here also. So I'll do it. So this would be 2. This should be 2. And also this one. I just plugged in the omega naught by 2. We can simplify it a little bit. We multiply by 2, and it would be pi times 1 plus j k 4 exponential minus pi divided by 2 minus 1. And I did those calculations by using the calculator just to find the value of this and divide 2 by pi and this and then minus 1. And then if we do these calculations, this will be written as 0. Now, yeah, I don't know, something is wrong with my scratch pad. 504 divided by 1 plus J4K. This is the decimal point. So 0.504 divided by 1 plus J4K. And this AK, those are the coefficients of the Fourier series for this function, or this periodic function, or this periodic signal. We can also do, you might be asked to plot, let's say, the first few terms of this. Let's say when K equals 0, then A0 will be just the numerator, so 0.504. And it's purely, just for this coefficient, it's purely real. So this is the same as its magnitude. And its phase is 0, right? Then let's say when K equals 1, then A1, I'm just plugging in when K equals 0, I just put K equals 0 here. K equals 1, put K equals 1 here, and then we get 0.504 divided by 1 plus J times 4. And if I multiply the numerator and denominator by the conjugate of this, we get 0.504 times 1 minus J4 divided by 1 plus J4 times 1 minus J4. And the denominator now will be just the magnitude of this number. Do you remember? Do you remember? Do you remember this?
Oh, that's the what is it? That's the difference of squares?
Uh,
No, sorry.
the addition.
I forgot. No,
It's the
I forgot.
difference of squares, right? But since this is complex, the square of the j will be -1, so it will be just the addition of the squares,
Hmm.
right?
I see. My bad. Yeah,
Yeah,
yeah, yeah,
you're
yeah.
correct. You're actually correct. You're correct. It's a difference of squares, but since this complex and the square of this j will be -1, so we get the addition of the squares. 0.504 times 1 minus J4 divided by 1 square plus 4 square, which is 17. Okay, I'm trying to find the magnitude of A1 and the phase of A1. Okay, the magnitude of A1 will be just 0.504 divided by 17 times the magnitude of this complex number. So 0.504 divided by 17 times the magnitude of 1 minus J4. And what's the magnitude of this? What's the magnitude of this number?
One, no, one line. No, yeah. Is it it's
It's
square root of 5? No, it's not square root of 15, right?
square root of 17.
17. Okay. Yeah, I
Yeah.
got it backwards.
Yeah, because here when we multiply the number with its conjugate, we get the square of the magnitude, which is this is the same number, the same complex number. So its magnitude will be just square root of 1 squared plus 4 squared, the square root of 17. And if we
J isn't included.
sorry,
The J is not included.
this is the magnitude, so it should be
Oh, never
real.
mind. Yeah.
Yeah,
I got it. Yeah, you're right. My bad.
yeah, it's okay. It's real. So if we multiply this term by square root of 17, I also ran this in the calculator, we get 0. Um, I hate those points. Those 0 point, it's a huge point, but 0.122. And this is the magnitude of this coefficient of the Fourier series. And its phase will be the phase of this or this. What's the phase of this complex number?
Would you have to take the tangent of like the imaginary part over the real part, I think?
Yes, yes, but the inverse of the tangent, so arc tangent,
Yes, right.
or tangent minus 1 of minus 4 divided by 1, which again, if you run it in the calculator, you get around 76 degrees.
Would you have to multiply that by 0.504 over 17 or no?
No, this is a constant real number, because if you multiply this by the complex number, it will be multiplied by the real and the imaginary. And if you divide them here, they will cancel.
Oh, okay.
Yeah, so you just, it's a common factor. It will not affect the phase. The ratio between the real and the imaginary will affect the phase only. But if both of them are scaled by the same number, this number will cancel from here. So, yeah. So the phase of this is 76 degrees. I'll do it for just k equals -1, and we'll stop here. If when k equals -1, there's a property when x is real, this xt signal, if it's real, we know that the coefficients, let me write it here. Since xt is real, then the coefficients will be there will be conjugate symmetry. or I think without this. So the AK will be the same as the conjugate of AK. So the magnitude of AK and A minus K, sorry, will be the same, but if we take the conjugate, then the phase will be just the negative of the phase. Negative. Let me write this. Since xt is real, we have this relation between the coefficients. So a minus 1, the magnitude of a minus 1 will be the same as the magnitude of a1, which we have found here, which is 0.122. 0.122, but the phase of a minus 1 will be negative the phase of a1. So the phase of a minus 1 will be negative 76 degrees. Sorry, this is the negative 1. If you run this in the calculator, you get negative 76 degrees, and this will be plus 76 degrees. Because of this conjugate symmetry, because the signal is real. So because the signal is real, the magnitude, if you plot the magnitude, whatever you see here, you will see here symmetrically. But in terms of phase, you will have this symmetry. Whatever you see here, you'll see it here. Is it clear?
Yeah, I think so. Yeah,
This is the
I
phase.
think so.
Yeah, this is the phase, and this is the magnitude. Because the signal that we are dealing with is real, you will always see this. AKs and A minus Ks will be the same values, but the phase, I mean here the magnitude of the AK and A minus K is the same, but the phase of AK and A minus K will be they'll be negative of each other, or this is the odd symmetry, or even. When a signal has this symmetry around the origin.
Is it
Like the sine.
is it even? I think.
Yeah, we need to check this. But yeah, so it's similar to the sine. So if the sine,
Yeah, so it's even, right? Or is it odd? I actually don't
yeah,
remember.
yeah, just confirm this, but you got what I mean. This kind of symmetry. Uh, whatever you get here positive, it will be reflected to this side, but it will be negative. Now let's plot those in an accurate way, just to make it clear. We always plot those kind of those coefficients in terms of k omega naught, because they are the harmonics of the fundamental frequency. So we plot them in terms of multiples of the fundamental frequency, right? So Omega not was 2, so K2 or 2K is better. 2K. We plot them in terms of 2K. And here I'm plotting the magnitude of AK, which is at 0, 0. Oh, not 0, sorry. It was this value. It was this value, right? So 0.504. Let's say here 0.504 at K equals 0. K equals 0. And then when K equals 1, we have a 2, like 1 times 2, which is, oh, this is when K equals 1. And similarly, when K, we get minus 2. When K equals minus 1. If we plug in minus 1 here, we get, if we plug K equals minus 1, we get minus 2. So it's at minus 2. So when K equals 1, we got A1, the magnitude 0.122. So something like this. 0.122. And then at K equals minus 1, we also got 0.122. And so on. If you calculate the next term, which is at K equals 2 and minus 2, you get something like this, smaller than 0.122, like this. And then the phase, again, we are plotting in terms of K omega naught, which is 2K. This is the phase of AK. The phase when K equals 0 was 0, because it's pure real. So we have 0 here. And then at K equals 1, we have this point here. It's 2, but K equals 1. And we get here minus 2 when K equals 1. And when K equals minus 1. When K equals 1, the phase was minus 76 degrees. So something like this. Minus 76 degrees. And when K equals minus 1, we got plus 76 degrees. And if you try to find the other terms, like a minus 2 and plus 2, a minus 3 plus 3, you will find that all of them have the same phase here, and also this at minus 2, minus 4, minus 6, 4, 6, and so on. yeah, it will continue with the same values in this side and on this side. Yeah, and that's all. I'll stop here. And if you have any questions, please let me know. I will stop the recording as well.